Okay, cool. So now take it away.
Okay, thank you. So I guess there comes a week where none of the organizers decide to be in Caltech. So, but I guess today I'm going to be talking about condensation, and in particular, um, the word condensation is very confusing among other words such as gauging, which is also what I'm going to talk about, or a duality. But hopefully I'm going to try to go through what different people mean when they talk about condensation and then how they're related. Here are some useful references. What I'm going to talk about is vaguely based on none of these, but they're sort of they're sort of put together through my confusion through the years. So hopefully it'll be somewhat helpful. And I guess maybe I have to declare that it also might be controversial, because I'm gonna introduce some words that have not appeared in the literature out of my desperation of no one defining one. So I'm just gonna make up some words and hopefully people will understand what I mean. So just to get started, what do we think about condensation? Well, the first thing we learn about in stat mech is Bose-Einstein condensation, right? And usually there we think of you have some bosons, you lower the temperature until at some point you gain some expectation value for a number of bosons in the ground state. And so you lower the temperature, you go through a phase transition, you find that there is some expectation value that is non-zero. So that sort of point of view is, if you talk to a condensed matter physicist, that's usually what they have in mind when you ask them what condensation is. And so that is one notion. So there are sort of two notions of condensation. One is more of a condensed matter point of view, and the second one will be a more high energy point of view. There are two things which people both call condensation. I don't have a better name for it, so I'm just going to come up with two names. The first one is the condensed matter one. I'm going to call Bose condense, because that's what we learn when we think about Bose-Einstein condensation. And let me just write down what this is first. As I just said, you tune some parameter and go through a phase transition, and then something gains expectation value. So of course, this is just like symmetry, some sort of like, you can think of symmetry breaking transitions as some sort of condensation of something, right? So most of like usual transitions you think of, they're all, you can think of condensing something. That's the first point of view. Now, the second point of view, which often you hear when you talk to high energy, is what you say you gauge a symmetry. You gauge some symmetry, could be some higher form symmetry, and the excitation you condense is the endpoint of some topological operator. So you have some topological operator corresponding to some symmetry. If you open it, you get some endpoint that you can think of it as an excitation. And by condensing that excitation, you would say you gauge that corresponding symmetry. I'm going to call this one gauge condense because it's gauging something. So to the best of my knowledge, this is, if you talk to different people, that's what they would tell you corresponds to condensation. Now, are these two things the same? There's a short and a long answer. The short answer is no, there are differences.
Can I ask, so when you say that gauging a symmetry, I mean, I'm familiar with the term that you're condensing the topological operator. Why do you say the endpoint? So I would think that if you want to gauge a symmetry, you should condense the excitation corresponding to the symmetry operator that's created by the endpoint, but not
That's created by the endpoint. Yes, yes.
The excitation which is created by the endpoint, not the endpoint itself.
The excitation. Oh, sure. I was
just
just being synonymous about that. Yeah, sure.
Yeah,
the excitation created by the endpoint. Sure.
Like if the endpoint is a point operator, it creates some particle, you condense that particle.
Yes.
Yeah,
That's what I meant. Sorry. Yeah. Right. So there are some differences between the two, and the most notable difference is when you both condense, the symmetry of your system is the same, because I tune through a phase transition. I never change the symmetry of my system, so the symmetry remains the same. Now, however, when you gauge condense, you're gonna gauge a symmetry. So of course, the symmetry you started with is gone, is gauged. But then you now have dual symmetry. So that's the most notable difference between these two notions of condensing. So, right. And so I'm gonna go through just basically one example today through the whole session. And I'm gonna talk about how to do condensation in the Tor code or Z2 gauge theory, and both by condensing and gauge condensing. And towards the end, I'm going to talk about how the two are actually related. In particular, you can think of gauge condensation as a modified version of Bose condensation. You can gauge a symmetry by tuning some other parameter, but the subtleties, I'll talk about that in a bit. Okay.
Yeah, can I ask another question about related? So when you're tuning some parameter such that some field gains it spontaneously condenses, spontaneously gains a VEV. So imagine you have a Ising model, you go to low temperature and the Z2 spin field condenses. But you could also turn on a transverse magnetic field, or in the high energy language, you could turn on some operator that explicitly breaks the symmetry. And that seems more analogous to the gauge, what you're calling gauge condensing, because there you also change the symmetry.
Or
sorry, you just add a magnetic field along the direction of the Ising model. Just add a Z2
the longitudinal, and that'll break the symmetry.
Yeah, sorry, not transverse, longitudinal. Yeah, and that will explicitly break symmetry, and that will explicitly change the symmetry, and you'll still condense your field. Is that how would you fit that sort of idea?
Let's see. By explicitly breaking the symmetry, I guess.
I'm saying that whenever you have something that gains an spontaneously expectation value, you could imagine something to prefer one versus the other.
Right. Right. But somehow here I want to preserve the symmetry while doing so. Yeah, I need to think about the case where you just explicitly break the symmetry. It becomes a little subtle in the context of like higher form, because those are emergent, so you can't really explicitly break them right away. But yeah. It's a good one.
I had a question about the Bose condense case.
Yeah.
So in generality, it's always some particle that's charged under some symmetry. And when you say that particle is condensed, does that always mean that symmetry is spontaneously broken?
So usually when you Bose condense, that symmetry is already spontaneously broken. And by Bose condensing, you're restoring the symmetry. By making it not spontaneously broken. Let me just, maybe after I give an example, it'll become clear. So the main example I'm going to play around today is going to be the Tor code. And this you can think of Z2 gauge theory, coupled to matter. Now, I'm not going to write down the usual Torah code Hamiltonian people usually write down. So in the Torah code, what people usually write down is you have a term called AV. For every vertex, you have a bunch of poly Z operators going sticking out of a vertex, and a second term called BP, which is a bunch of poly X's sticking around, going around each plaquette. The Hamiltonian I'm going to write down is that I want to consider this. So of course you can write down the Hamiltonian, which enforces both of these terms to be one. But here I want this to be a Z2 gauge theory. So I'm going to enforce that I have a constraint where BP is always equal to 1. And this is a constraint that will forbid any flux excitations. So this is sort of you can think of it as a gauge constraint if you want. And we're only going to be in the gauge invariant subspace where BP is equal to 1. And so my Hamiltonian will only be this consisting of enforcing the vertex term. And then I also have some parameter lambda where I allow some transverse field X. So that'll be my Hamiltonian. And you can think of it in terms of Lagrangian if you want, that I have some ADA type of term which mixes like electric and magnetic one form, right? And then I only allow charges. I only allow electric excitations. I don't allow magnetic excitation. So you might remember from Sal, when Sal talked about one form symmetry a while ago, because I enforce this BP to be 1, in this model, I'm going to get a topological one form symmetry versus this sort of faithful one form symmetry. So because BP is equal to 1, I can define a one form symmetry, which is a product of X's all for any closed loop. So for any E in some one cycle. And you can sort of think of this as being -1 to the AE around the closed loop. So this is just your one form symmetry, and you can deform it because BP equals 1 allows you to deform the string. And note that this is the electric one form. And note that there's no magnetic one form for lambda not equal to 0 because the charges spoil this magnetic one form. Okay. And just to make sure what I mean by my electric charge here, so the charge E is just a violation of AV being -1. And so if I have some lattice and I apply an open version of my Wilson line, which is a bunch of X's, then it's going to, and this is my line, it's going to violate the vertex term here and here, and that is what I call E. Okay. So far, so good. So now let me talk about first the Bose case. So when we do Bose condensation, what I'm going to do is I'm going to turn lambda to be large. And so it goes through a phase transition. And this lambda, the term is exactly XE. And so what it's doing is it's going to promote. So what does X do? X sort of wants to create pairs of two E's. So if I tune this lambda to be large, it's going to promote proliferation of E's all over your lattice. And once lambda becomes large enough, you're gonna just get a superpositions of all E, so that an E excitation is not topological excitation anymore. So that's the notion of which E is condensed. So in particular, if I take the extreme lambda goes to infinity limit, well, what happens then? H lambda will be effectively just this term. I just throw away the vertex term, and I'm just left with xe. Note that we still have BP equals 1. And note that in this case, we still have the one-form symmetry, right? Because the Hamiltonian, actually the Hamiltonian for the whole lambda, it commutes with this. It commutes with this electric one-form symmetry.
Sorry, isn't that the symmetry? Wouldn't that be usually called the magnetic one-form symmetry, and vice versa?
Let's see. I always switch them, so you might be right. Let's see.
The one you're preserving, you have electric charges proliferating, right? So that should break what at least I usually would call the electric symmetry. Whereas you're preserving, I think the one we would usually call magnetic symmetry. Which is
okay, sure. It might just depend on convention on what you call.
Yeah.
Whether the electric is detected by the magnetic, or you call the electric.
Yeah.
Sorry, it's one of them. I will never get it right. So maybe that's a. Sure. Yeah. Sorry about that. Let me just say this one, the one defined by this, and I am also not. I can't check live, but I'm not sure whether this should be E or M either. The way I've written it here.
I think the symmetry which is preserved as you've written it is the topological operator is the Wilson line, and it generates the symmetry which is broken by the presence of M particles.
Right. So maybe I should have written this as M, because I want the one. Let's see. I want to call the endpoint of AE to be E.
Yes.
Is that okay? So maybe this should be M. Is that AM? But I should call.
No, I think what you said. I think what you said is right. Right. The line operator for whose endpoint is the E particle is this generates the symmetry which is broken by the presence of M particles because of the linking between E and M.
Yeah. Right. Yeah, sorry for the notation confusion. Yeah.
I just want to make sure I'm understanding you correctly.
Yeah. And let's see. Right. So just to continue, in this lambda infinity limit, the Hamiltonian is just a product state, right? You just have disentangled. You just have every qubit is disentangled from each other. You still have the one-form symmetry, and so now you'll have an expectation value of something that looks like product of X on an open interval C, like open, which you can sort of think of like some disorder operator like mu I, mu J for I, J separated, and then this value is sort of non-zero. So that's Bose condensation. Any questions until now? Okay. So let me discuss the gauge. And this will be a much longer discussion because, yes.
Just to confirm, so in this context, there is no spontaneous symmetry breaking when you say Bose condensation.
The toric code itself already spontaneously broke the one form.
Right.
And by condensing, I restored the one form.
Not one form. We're not talking.
Sorry, yeah, I couldn't quite hear. Did someone say something?
I think Shia said something.
Hello?
Oh, sorry. I didn't realize I'm. Okay, so Nandu, are you asking about the one form or the global one?
The global one.
So here there is no zero forms symmetry.
Right. Yeah.
Right. So I think Nandu is asking. So in terms of like boson condensation, originally we had a global U1 symmetry, and then you spontaneously break it into the condensate. So the toric code, the corresponding picture would be there was originally a global Z2 symmetry, but it's gauged. So now there's no global symmetry anymore, but effectively, you can think of the matter field as spontaneously breaking the global Z2. And is that what you're asking, Nandu?
Yeah, that makes sense. Thanks.
Okay. Sorry.
Yeah, maybe you could call this Higgsing or something, right? This is your spontaneously
yes.
the gauge symmetry, which
Yes.
Yeah.
Yes. Right. So you can call it either Higgs or confined, depending on whether you think of electric or magnetic. But yeah, there are too many ways you can turn the picture around to confuse everyone in the audience. Okay. Any other questions? Okay. So now let me talk about gauging. And what we want to do is I have a one form symmetry, right? And now I want to gauge this one form symmetry. So what I do is I want to promote this one form to a local symmetry. So what you want to do is you couple to a two form gauge field. And usually two form gauge fields live on plaquettes of the lattice, but due to the way I've drawn the picture, it will actually be the plaquette on the dual lattice, which is actually equal to the vertices. So so I'm actually going to introduce gauge fields on the vertices instead of the plaquettes. And you'll see in a bit why it's more natural when your E, the E string moves on the direct lattice. So so the gauge field here is also a qubit. And so it has Pauli operators X and Z. And if you're more familiar with the U1 version of things, you can sort of think of X as being some exponent of the vector potential, and Z being your electric field, right? And the fact that X and Z anti-commute is sort of the analog of E and A having this commutation relation. This is just a Z2 version. So instead of the U1 version and then exponentiate everything, I'm just doing a Z2 version. So now I just have X and Z operators and the anti-commute. Okay, so I have my symmetry, which is like a product of X along some cycle. I want to promote this to a local symmetry. So what I can introduce is this Gauss law on each edge, which looks like the following. So for each symmetry action XE, I add something. So I've added a gauge field on each vertex, and now I'm acting with this Pauli Z. So just so that people who usually think about U1, what is XE doing? Well, XE is sending ZE to minus ZE, and that's the analog of you have some field like psi X, and then you're sending to minus psi X, right? So that's the action of the symmetry, sending psi to minus psi. And now ZV, that's sending XV to minus XV. And you can think of it as I have some two-form gauge field A, and that gets modified to A plus D phi, where phi is a one form. And so, right, so it lives at the endpoints and this boundary co-boundary operator is just saying it's living at the endpoint of this edge. So this is the analogy. And now note that with this local symmetry operation, you can restore the global one-form symmetry by noting that if I multiply all the GEs on a closed loop, then I will get back my global symmetry action, which is E and C. So the Z's just cancel, right? So the gauge transformation on the closed loop, right? Because you're taking a boundary of a boundary, it's a co-boundary of a co-boundary, it cancels, and so you just restore your one form symmetry. Okay. So that's local symmetry action I'm going to impose. Okay. Now let's look at our Hamiltonian again. Our Hamiltonian was this one. Just copy it. Now, this XE term already commutes with your Gauss law, so that's fine. But this term, you can think of it as a kinetic term, but for the one-form symmetry, it doesn't commute. So your kinetic term doesn't commute, so you have to do minimal coupling to make it covariant. So if I minimal couple, you can notice that this thing here now commutes with my Gauss law. So because my Gauss law looks like ZXZ on each edge, right? For every edge, you're going to see that you have X and Z meeting twice. For example, for this edge, you're going to meet here and here, so it's going to commute. So now it commutes with the Gauss law, right? And the analogy is, well, you have some sort of like kinetic term, right? And you sort of couple it to a gauge field, right? That gauge field is living on the vertex such that now this, you just covariantize it such that it's invariant under the gauge transformation. Yeah. So this you can think of as a gauge transformation.
So the idea is that you want to rewrite the Hamiltonian so it commutes with the Gauss law, and then are you going to impose Gauss law as a constraint?
Yes.
Yeah. Okay.
Right. So exactly what Jake just said. Now let me write down a modified Hamiltonian, which is the minimal couple Hamiltonian, which will now look like this, right? Minus lambda XE. And I'm going to impose it with the constraint GE, which is this guy, equals 1 for all edges. Okay. So this is the minimal couple Hamiltonian. So by doing so, I have gauged the symmetry. Any questions until now? So, yeah.
You don't have dynamics for this gauge field?
I do not at the moment, yeah.
Okay.
Okay.
Because it's a two-form gauge field in 2 + 1 dimensions.
Yeah, there's nothing much you can do.
I see.
Okay. So there are two ways to simplify this Hamiltonian. The first which might be more familiar to people, is gauge fixing. So let me talk about that first. So what we would do is we view GE as a gauge transformation between like gauge equivalent configurations. So the physical wave function will be a product of all possible applications of GE to some wave function. And by gauge fixing, we just need to pick one of these as a representative. because we can go through any other equivalent configuration by acting with GE. Okay, so we can note that this GE flips the value of ZE on each edge, because for each GE you have a poly X on each edge, so it's going to toggle the value of Z on each edge. So to gauge fix, we can choose a gauge where ZE equals 1, right? Because we can go to any other value of ZE but just by acting with the GE, the gauge transformation. Okay, so now if we do this, the minimal couple Hamiltonian, once we gauge fix, so first this term here has a bunch of Z's on each edge. We've set Z equals to 1. So we're just going to get a single X left on each vertex. And now the second term, it's already XE, so that's fine. But we note that using GE, which is ZXZ, I can replace this with ZZ for each edge. So this is up to GE. And now we notice that this gauge fix Hamiltonian doesn't depend on any of the edge degree of freedoms at all. And now we find that, well, this is basically just the Ising model. Okay, so by gauging the one-form symmetry of this gauge theory, we obtain the Ising model in 2+1D. And there is a dual zero-form symmetry given by flipping all the spins on each vertex, which is given by XV. Okay. So that's one way to view it, by gauge fixing. A second way it's something. Oh, and any questions up until now? Hopefully this is the more familiar one to people.
Just so I understand, right? So we started with something which was like Z2 gauge theory plus Z2 matter, and then you've gauged the one-form magnetic symmetry, and you're just sort of left with the Z2 matter. Is that the idea?
Yes, you can think of it that way, I think. Mm-hmm.
In some sense.
Yeah. Okay. Now, the second way I'm going to think about it is something I'm going to call integrate out matter fields. Now, I put this in quotes because what I mean by matter and gauge is going to be a little confusing, because what I mean by matter here is something that transforms under the symmetry I'm gauging, and that is the one-form symmetry. So the matter I'm talking about is the stuff on the edges, which would usually be the gauge field in the gauge theory. But nevertheless, I'm going to call it the matter field. And what we're going to see is that, well, as we've seen by gauge fixing, is that the gauge field I introduce to gauge the one form now becomes a matter field of the zero form symmetry. So there's some duality in what you call gauge field and what you call matter field. So there might be some confusion here, but hopefully matter field here, what I mean is of the one form symmetry. So I mean degrees of freedom on edges. Okay. Now, I guess usually when we talk about gauge fixing, the reason we do that is because, well, the gauge bundle is usually non-trivial, so we can't pick a nice section to describe our theory to begin with. But it turns out in this case, the gauge bundle is actually trivial. So you can actually completely decouple the gauge and matter fields entirely. And that means that you can just pick a section and then you're good. So what I'm going to show is there's a unitary to set that turns your Gauss law into a single XE. So it just acts on each edge. And once you've done that, then you can just decouple you can just set this equal to 1 separately. And that's what I mean by like integrating out the matter field with one form. So you'll just be left with your pure gauge fields. So there's 2-form gauge fields, which now will become the constituent of the Ising model we were looking at. Okay. So this might be less familiar. This unitary turns out might be less familiar with for high energy people, but I'm just going to write it down and then explain it. It's something called a control Z operator. So I'm already borrowing lingo from quantum information, but you can just take. Let me just tell you how this operator acts. Let me not explain the lore of this operator, why it's called that way, but it acts on 2 qubits, for example, V and E, that's vertex and edge. And so the complete basis of Pauli operators I can write down is the following. Z, E, Z, V. And this action is just given by, for each X, you append a Z on the other qubit, and you leave the Z's invariant. You can convince yourself that this is a unitary because it preserves commutation relation of these operators, and these 4 span sort of the full algebra on 2 qubits. So it preserves commutation relations, and so this is a unitary operator. And now basically this unitary, what I'm doing is, for my lattice, I have stuff on vertices and edges. For each vertex edge pair, I'm going to apply this control Z operator. Okay.
Last one, you mean IEZB on the left side, right?
Oh, yes, thanks. IVZE. Yes, IVZ. Yeah. So note that this control Z guy is symmetric, so it doesn't matter which one was the vertex and which one was the edge. Okay. So now let me copy this minimal couple Hamiltonian. Oh, and I should mention this is an order 2 operator, so stuff goes backward like this as well. So first of all, let's see that the Gauss law disentangles into X. Well, if I apply this gate to all edge vertex pairs, then you see that ZX is just going to become identity X, right? So I'm going to get identity X, and then now I act with this pair, I get identity X. So I've just reduced it to X on each edge. And now for the minimal couple Hamiltonian, you applied for all these pairs, and then you'll see that this reduces to, so U dagger is X. And now for this term, for each X on each edge, right, that was transverse field I applied, I'm going to act on this twice, and then I'm going to get ZXZ for each edge. Okay, this is UGU dagger. But now once I have such an expression, I can just set UGU dagger to be 1 because they're completely decoupled, right? So set this to be 1, and then I'm going to get minus XV, and then I'm just going to kill this guy because XE is set to 1. So I get my Ising Hamiltonian back. I see. Okay. So
that's familiar. Can you remind me? So lambda here, just matching parameters. Lambda here is like the spin coupling is the idea.
For Ising, yes.
Yeah, for Ising. And then the first term would be a transverse field.
Yes, yes. Okay. So just to conclude what we've done, I started with the toric code, and then there's some parameter lambda. Right. The toric code is in the deconfined phase. And once lambda becomes large, it's in the confined phase. And when I say I Bose condense, I'm just tuning this parameter to induce a transition. On the other hand, I can gauge the symmetry, and you can call it a gauge condense. And you'll get the Ising model with the same parameter lambda, where here you would have started in the paramagnet phase, right? Because when lambda is 0, you're just going to get a paramagnet. And when the ZZ coupling is strong, you get the ferromagnet. Now, the slight confusion stems because both of them give you some sort of short range entangled state. So both are valid in terms of proliferating these E anion excitations, right? But they're sort of different in the sense that one of them, you're not changing the symmetry, and one of them, you're gauging the symmetry. It even becomes more confusing in 1+1D, because in 1+1D, let me just put that in. So in 1+1D, this would have been the ferromagnetic phase, and this would be the paramagnetic phase. And moreover, these are these are sort of equal. So in 1+1D is most confusing because they look exactly the same when you do that. But the subtlety is, one, you didn't change the symmetry, and one, you're talking about another bottle with the dual symmetry, like Jake was talking about last week. So that's why I intentionally did it in 2D so that it won't be as confusing, and you actually see the difference. The symmetries will be different because here I've explicitly chosen the dimension of the form to be different. Okay. So hope that demystifies things to some level. Let me also comment that for gauging, you can also go reverse, in the sense that if I start here, you can also gauge a zero form symmetry to go back up. And what are you condensing? Well, you can think of the symmetry operator ending in a domain wall. So you're actually condensing domain walls to go back up. What is the Bose condensed version of that? Well, if I start with the ferromagnet and I Bose condense domain walls, then I would end up in the paramagnetic phase. But I can, when I gauge, it doesn't matter which part of the phase diagram I'm in. I can gauge condensed domain walls. Either I'm on the right part of the diagram, the left part of the phase diagram, it'll always bring me up. It doesn't matter. Yeah. So yeah,
I think I'm still caught in the trap that you said we sort of were stuck in, that these things are they're both proliferation of the same object. So how do you think about that, about the difference in that sort of just intuitive proliferation object?
Right. I'm about to, the thing right after this is how to relate the two. So maybe that'll address your confusion. So any questions up until now?
You can also think about the paramagnet to ferromagnet transition as Bose condensation of particle excitation.
Yes.
Does that also translate into some version of gauge condensation?
That's more subtle because let me see. The charges are created by ZZ. And so what's the corresponding symmetry operator? That's a one-form symmetry. So it's a bit, it's a little bit subtle, but I think it is possible to gauge, but on the lattice it's a bit confusing. Like there is a weird one-form symmetry in the Ising model that you can gauge. That gives me a little a bit of uneasiness.
Okay.
Yeah, and it's not there always. Depending on where you are in the phase diagram, this one-form symmetry can be broken explicitly. It's not clear whether it's emergent to me either. So I'm a bit unsure. Yeah.
Is it important here that the objects you're talking about, Bose condensing in both of these cases, are objects charged under a gauge symmetry, right? The boson in the toric code that you're Bose condensing is a gauge charged particle, and the domain wall in the ferromagnet carries a gauge charge in the sense that on one side of the domain wall you have a spin up, and on the other side a spin down. You can view that as a gauge charge. So when you're talking about Bose condensing, is it specifically Bose condensing objects that carry gauge charge?
Let's see.
The other example of condensing the spin in the paramagnet to get to the ferromagnet is Bose condensing a particle
with an actual charge,
which is not a gauge charge, right?
Yeah. True. Yeah.
Sorry, in what sense is the excitations, for example, the domain wall gauge charged, or the?
Yeah. So the one way to think about gauge charge is that an object has a gauge charge if you can detect it from far away, if it radiates some flux. And the domain wall in the ferromagnet radiates the flux that on one side is the spin up and on the other side is spin down. And so if you were really only looked far away from it, you could tell that there was a domain wall there, or an odd number of domain walls, because on one side you have spin up and on one side you have spin down. So you can view that as a domain wall gauge charge. I guess here it's a two-form gauge charge.
Just to translate that into condensed matter language, is that equivalent to what we call a topological excitation?
Yes. Yes. In particular, in the Ising model, in the ferromagnet or in the paramagnet, the domain wall defect operator links with the local spin operator. With the spin, that doesn't sound quite right. Sorry, domain wall is a surface operator in 2+1D. Yeah, so it links non-trivially with
Okay.
In other words, it's remotely detectable, I think is the word that I should maybe use.
Right. Okay.
Okay. Any other questions? Otherwise, I'm going to talk about relation between this gauge condensation as modified Bose condensation. So just to recap, Bose condensation, I never changed the symmetry, right? Gauge condensation, Bose condensation, I never changed the symmetry. Gauge condensation, I gauge the symmetry, I get a dual symmetry. Is there a way to get this gauge condensation from a particular Bose condensation. Well, naively, you might think, well, if you want to preserve the symmetry, well, the gauge condensation is going to change the symmetry, so I can't do that. But what you can do is, so I start with my Tor code. I add some new degrees of freedom with transforms under my dual symmetry. So then if I do that, now the whole system will have a symmetry that matches the target thing I wanted to gauge, which has a dual zero form symmetry. So then I can tune some parameters and go through a phase transition. That'll be condensing something, which I'll talk about. But then you can think of gauging as a particular Bose condensation. Okay. So what I'm going to do is introduce ancilla degrees of freedom on vertices. We already saw that from when we were doing gauging. These are what I called gauge fields. These are the gauge fields earlier. But now let me just call them ancilla degrees of freedom, stuff you add for free. And in particular, this ancilla will be governed by a Hamiltonian, which is just minus xv. So it is a paramagnet. It's in the fixed point paramagnet of the Ising model. And in particular, it has this dual zero form symmetry that I want to get at my target. Okay. And now note that this zero form has physical charges. The physical charges are stuff that transform under, this is Z2, so it's stuff that transform under the sign rep of my symmetry. So that's a poly Z. So Z on a vertex, right, it gets flipped to minus Z under X, so that's my physical charge. And I can create a pair. So I can't create one at a time, but I can create a pair with ZZ because that's two odd charges, which is even, and that's exactly the Ising term. Right? So the interpretation of the Ising term is creating two charges at V and V prime. Okay. So now let's revisit this gauging. So Gauss' law I imposed was like ZXZ, right? So suppose I had a system and I turn on the Gauss law to be very strong, right? That's going to enforce me to be in the gauge invariant subspace automatically. So once I turn this term to be very strong, I'm going to go through some transition. So I want to think of this as condensing something. So turn on GE to be infinity. Sorry, maybe I shouldn't say infinity. I have some term like big lambda, and I turn lambda to infinity. Is condensing something. Well, what am I condensing? The X, right, is creating two E's. That's my anion and the citation of the Tor code. Let me call the physical charge here C. That's the physical charge. So ZZ on each vertex is creating two C's. So by imposing this, what I'm condensing is the pair EC, right? So instead, let me make it clear. I'm both condensing the pair EC. To be more precise, I should put an inverse here, but it's Z2, so it doesn't matter.
C is the ancilla?
C is the charge of my ancilla, which has transformed under zero form symmetry. So intuitively, right, I'm proliferating these as bound as pairs, as bound pairs of a gauge charge and a physical charge together. So that's the difference. Now, if I do it this way, what happens? Then if I Bose condense this bound state in the condensate, it means that EC inverse will be equivalent to the trivial particle. And that means that E will be equivalent to C. So by doing Bose condensing this bound state, I associate my gauge charge now to a physical charge of the dual symmetry. And now that's why this gauging is doing what it's doing. It's turning the gauge charge into a physical charge. And here is a prescription of how to realize that by introducing some ancilla with a new symmetry and then tuning some parameter to do the condensation, to do the Bose condensation. Okay, so just so that it's crystal clear, let me do that at the level of the Hamiltonian to see how it comes about. So my H total will be the original Hamiltonian plus my ancilla, and that'll be, I have my original toric code Hamiltonian. I add some ancilla, which are these on the vertices, right? And then the top part has this Gauss law constraint, sort of. Okay. Now, then I add condensation term that is minus lambda G, that's my Gauss law, right? And tune lambda to infinity. So if we tune lambda to infinity, then we want to compute what is the effective Hamiltonian in the subspace where lambda is infinity. So to do that, we need some degenerate perturbation theory. This is not, it's not actually not that bad. When I say perturbation theory, some people get scared. But actually, basically, because everything are Pauli operators, you only need, you'll get some higher order matrix element, but those matrix elements are basically, you want to product all the terms which will now commute with the Gauss law, right? When we do perturbation theory, we just say, okay, at 0th order, what commutes? So this term already commutes, that's fine. First order, there's nothing, but at 2nd order, we're going to have this term times this term, right? And together, that gives me this term. And that commutes with the term I impose. So I get this at 2nd order with some coefficient that's not very important to us. But now you notice that by doing perturbation theory, this is exactly what we mean by minimal coupling. Right. Our kinetic term didn't commute with the Gauss law. So we found some modification to make it commute. And that term is exactly this guy. So perturbation theory automatically gives you a minimal coupled kinetic term by doing this. So in the effective Hamiltonian you'll get will just be, well, if you took care of the coefficients carefully, probably 1 over lambda. And then this term already existed. And you're in the subspace where GE is equal to 1, right? And note that when GE is equal to 1, this plaquette term is already satisfied, so I don't need to write it again. Because if I multiply GE around the plaquette, I restore this term, so I don't need to write it again. Okay, and so we recover the minimal coupled Hamiltonian. And now you can do your gauge fixing or like integrate out your matter field to get the Ising model. Okay.
So here you're imposing the Gauss's law energetically, and you're saying this is a form of Bose condensation.
Yes, yes. Because I'm tuning some parameter to be large. What is that Bose condensing it's the balance state of my gauge charge and my physical charge. Yeah, so the trick was to introduce a dual symmetry from the beginning. So that's where the symmetry changes. But from then you can tune and keep the symmetry, the new symmetry intact.
In terms of the symmetries, so the ancilla you added have Z2 topological zero form symmetry, and the original toric code had Z2 topological magnetic symmetry, one form magnetic symmetry. And then adding this condensation term, can you just say, it's probably obvious, but how that affects those symmetries? I assume it preserves the zero form and breaks the one form or something?
Well, the one form becomes local, right? Because the Gauss law is
Oh,
the
it gauges
local.
the one. I see.
Yeah.
Well, at low energies.
At finite lambda, what would you say happens?
At finite big lambda, you mean?
Finite big lambda, yeah. That sort of one form. You still have that one form topological symmetry, right? Or do you not?
yes. Wait, let's see. Let's see. I think still have. I mean, how should I say this? I mean, throughout the phase, throughout the parameter lambda, right? You always have this. It commutes with this whole Hamiltonian I've written down. It's just that when you go to this limit, then sort of like this is already redundant with. Maybe it acts trivially in the subspace where G equals 1, so you don't need to care about it. Maybe that's the way to say it.
Right. So
it's still there in the full Hilbert space, but I'm only considering this subspace, and that's exactly the gauge invariant subspace.
Right. So the gauging is supposed to get rid of your original symmetry and add a dual symmetry. That's how the symmetry changes. And so if you add the dual symmetry from the get-go, you sort of have both the symmetry and the dual symmetry at once, and you can sort of just tune from one to the other by Bose condensing. Is that the point? Yeah. Okay.
Yeah. And actually, maybe I should also comment that, you made a point that by introducing this symmetry, I have both the original symmetry and the dual symmetry. And that's exactly the perspective of this paper, where they talk about Higgs condensation and relation to SPT. So you have both the original symmetry and the dual symmetry, but the state you have at the moment when you introduce the Gauss law can be in a non-trivial SPT protected by the original and the dual. So that's the perspective of this paper, which you can check out if you're interested. Yeah, but in this guise is all sort of related to minimal coupling, and then and this unitary actually that I use to decouple is exactly the unitary that takes you from the non-trivial SPT to the trivial SPT. So this like integrating out of matter field, you sort of have to apply some unitary. The unitary actually doesn't respect the zero form times one form symmetry. And so that is why you can you explicitly break your SPT symmetry to go from trivial to non-trivial.
I have sort of a conceptual question. So when you have a symmetry spontaneously break, I mean, we sort of think of that as condensing. And if you look at fluctuations around one of the symmetry breaking vacua, you no longer have your symmetry, right? That's sort of what, of course, if you include the multiple vacua, you still have your symmetry, but if you look at fluctuations around one. So somehow, I mean, the sort of modern dogma is that spontaneous symmetry breaking is not symmetry breaking, right? You still have your symmetry. But in some sense, if you just look at fluctuations around one vacuum, you sort of effectively have broken your symmetry. And I wonder if that's sort of related to some of the things you talked about. Do you have thoughts on that?
Not immediately. Let's see. So yours. Let me try to understand. Like
you're this sharp distinction between Bose condensing and gauge condensing. And I wonder if it's sort of like the difference between viewing spontaneous symmetry breaking as leading to a system with both vacua versus one, looking at fluctuations around one vacuum. Maybe I need to think more about how.
Yeah, I don't see the immediate connection yet, but maybe
sure,
we can chat more about it. Okay.
So, maybe one more question. So
Yeah.
So because this is like 2+1D Z2 gauge theory, right?
Mhm.
Principle, there's a Digraph-Witten term that one could add.
Yep.
Do you know if the whole story is affected by that, or like can you?
Oh yeah, I was about to comment about that. So if you did Bose condensation, you would just get a trivial state, like some confined state. You can condense the boson in the Digraph-Witten theory. But if you gauged it, then you would get a dual symmetry, and then you would have a non-trivial SPT protected by it. So somehow gauge, I just advocated, well, you can think of gauge as some particular Bose condensation, but yeah, in some sense, thinking of gauging is sometimes a bit better, because you keep track of the dual symmetry. And of course, if you forgot about it, then you would say, oh, it's trivial. But if you remembered it, then you would say, oh, it's a non-trivial SPT. So I think that's the advantage of thinking about gauging, rather than just turning on a term in the Hamiltonian. But of course, if you do it the right way, you can do it such that it's gauging. Right?
You mean gauging in the sense of Gauss law, not just gauging sort of energetically.
Gauging
by opposing Gauss law as an energetic thing versus
well, by imposing Gauss law energetically, I mean that's basically what I'm doing here, right?
Right.
Okay. Which is a particular Bose condensation, but it's not Bose condensing that anion. It's Bose condensing a bound state of that anion with a physical charge. My point was just that if you do Bose condensation properly, it will be equivalent to gauging, which keeps track of more stuff, in particular the dual symmetry. So it's useful to do that rather than just usual Bose condensing.
Yeah, something else related to I know there's this notion of sort of fermionic condensation in topological orders, where you condense a neutral fermion or something.
Yeah, you guys keep coming up with points I was about to say.
Oh, sorry.
No. That's a good thing. It's a good leeway, because I was about like, okay, here and now a couple comments. I'm gonna finish talking, and then you ask about like a Witten term, and then you ask about fermion condensation, exactly what it was about to comment on. Right. So, right. So there's something called fermion condensation. Right. The main thing is done now, and after this is just comments. So there's something called fermion condensation, where if you think of Bose condensing fermions, that doesn't make sense because, well, they're fermions. And well, if you gauge it, well, the corresponding symmetry is anomalous, so you can't gauge it. But if you went ahead and did it any way, then you'll get a spin theory. So you'll have physical fermions. Now, what is that? How do I do that in terms of a Bose condensation? Well, what you do is, the statement is that suppose you have anions that are fermions. So for example, in the Torah code, you can have like a bound state of E and M, right? Which you can call fermion. The particular lattice string operator is not important. But you can't couple this to a two-form gauge field consistently, because the hopping of fermion this way is not equivalent to fermion going that way. However, what you can do is, that's if I introduce my two-form gauge field as a qubit, right, which is a boson. But now it turns out if you introduce your gauge field, quote unquote, your two-form gauge field as a fermion, then the hopping together will make sense. And what you're condensing is emergent fermion F with physical fermion psi. So the story is analogous story. I introduce physical fermion that makes my theory spin from the get-go, right? And then I can condense this pair, which is a boson. But it's sort of intriguing on the lattice in the way you do it, because now you would think, if you would think of it as gauging, your gauge field is now a physical fermion, which is something I don't usually think about, but it feels like it's something cool.
Is this related to like having a spin, like a spin C gauge field, like the quantization?
Let's see. Here it's sort of like the gauge field I introduce, like on each vertex, is a physical fermion, right? And then after I do all the stuff, it becomes the matter of my fermionic theory. I'm not sure. When you say as a gauge field is spin, you mean
Spin C.
It's already combined with some choice of spin structure, I guess. So some extension of U1
Right.
by. I feel that's different, because that's what you would do when you start with the spin theory and then couple to a gauge field, right? So I feel that's the going the other way.
Is part of this the lesson here that maybe you should only ever consider Bose condensing topologically trivial excitations, like in the first example in the toric code, you wanted to condense the E particle, which is not a topologically trivial particle, right? It it's an anionic excitation. But you added your ancilla, and then the combined thing is like maybe a topologically trivial thing. Again, here I guess that's not quite right, but
yeah, it's not really topologically trivial, but you want that thing to be trivial, so that sets the two to equal each other.
Right. Yeah. Is anion condensation, would you call that Bose condensation or gauging gauge condensation?
When people talk about anion condensation?
Yeah.
Depends on who you talk to. I think I've heard of both.
I see. Yeah.
Yeah, it's confusing depending on who you talk to. So I have to always ask them which version they're thinking about. Yeah. Right. If you're interested on how to do this on the lattice, feel free to check out this paper. 5652. There are other papers which consider this more formally, but this one, which I wrote with some people, does it explicitly on the lattice if you're interested. Is there any more?
You mentioned Jordan-Wigner duality in the beginning. Is this fermion condensation somehow related to that?
Yes.
Okay.
So yeah, there's also a whole other like confusion about what is duality, and if you're confused about that, I recommend this paper by Radicevich, where, for example, for like, you often hear people say, oh, the Ising model is dual to the toric code. What does that dual mean? And he talks about different versions on which they're not equivalent or equivalent, or what subtleties he made. So the same, that's what people usually call Kramer's one duality, but to make it precise, you have to modify it a bit. And he talks about 3 different versions of the same thing, which are different versions of Kramer's one duality that are well defined. So I can also talk about that, but I don't want to keep people. So, but I recommend taking a look at that paper. Any other comments?
Maybe a sort of broader conceptual thing here is, what we're being really careful about here is what are our symmetries and how do the symmetries act? And for example, when we think about SPT phase as being different from a trivial phase, is because it's, we fix a symmetry action or something.
Yes.
But and there's a lot of good reasons for that sort of modern perspective. But I wonder whether it's sort of putting the formalism before the physics in some ways, because a choice of how the symmetry acts, it's not completely obvious to me that that's a property of the physical system. And this goes back to something we talked at in one of the first few weeks about the idea of, is symmetry a property of the quantum system, or do we fix our symmetry and then look at quantum systems with symmetry? And I think this is sort of going towards in the second case. It's not that the symmetry is necessarily an intrinsic property of the physical system, but maybe it's you fix your symmetry and then you look for physical systems with that symmetry, and that's when like in particular, there's sort of old confusions, and some parts of literature are very confused about, are theories that differ by discrete gaugings, are they the same theory or not? And the modern perspective would say that not necessarily, but
you mean discrete torsion or discrete gauging?
Just discrete gauging, like these Kramer-Steiner duality type things. And, yeah, I guess I just worry whether the modern perspective is missing something. Is putting formalism first too much. I don't know.
Yeah. I mean, you can make them equivalent if you restrict to some sector of the symmetry, and then they're equivalent. And that's exactly the viewpoint of this boundary topological order as a shadow that Shogang's talking about. Yeah.
Oh, I see. This is a sort of SymTFT picture.
Yeah, it's a SymTFT, right? If you restrict to the symmetric sector, then they're equivalent.
I see. Yes.
Right. So if you mod out by this equivalent symmetries, and they're dual. But then you can also multiply one to the other one, and that's coupling one side to a gauge theory, and then now it's dual to the original one in the full. That's exactly the three versions, right? You mod out by both symmetries, you multiply this on one side, and you multiply this on the other side. So, and those are three versions of Kramer's Wania made precisely. If you want to be exact about it.
Yeah. Thanks. That definitely helps.
Let's see. I guess
Yeah. I was just going to ask if there are any more questions, but if you have something more to say.
Yeah, I guess neither of us have got into higher gauging yet. Is that correct?
Higher gauging? No. Maybe, do you want to ask for volunteers and talk about possible future topics?
Yeah. So I guess there's not that many people around, but I think there's two topics that we haven't covered. I guess many topics. One of them is, as we were saying, higher gauging, which is gauging of some of these new notions of symmetry. Even before that, just the notion of higher groups we haven't discussed kind of jump directly into non-invertible symmetries, because I ran out of time to describe at least what a continuous higher group was. But,
and because non-invertible symmetry is what I wanted to talk about. So
but I think there's no order anyway between these things. And then there's also something that we were discussing, which there were a few papers that appear over the last month or so, which look very interesting, which is the idea of higher representations, or it's just the fact that, okay, we always think about zero form symmetry acting on local operators, one form symmetries acting on lines. But of course, if you have a zero form symmetry defect, you can still ask what happens when I make a line go through it. So actually, like the different defects, they naturally act on the things that they link with, but they can also act on other objects.
A very simple example of that is, electromagnetism has a charge conjugation symmetry, which takes the Wilson line of positive charge to the Wilson line of minus charge. So that's an action of a zero form symmetry on a line. So
that's right. Yeah. So I think there's been some very recent understanding of kind of the big picture of how do the defects of different dimension act on each other, and I think that would be also nice to have some discussion about. So we kind of are repeating over and over again that we have this kind of higher categorical structure, which is just the set of topological operators and how they fuse and how they talk to each other. and then when you act, how they act on other stuff, then which is not topological, then I think this notion of what is a module over this category of defects, or like what is a representation of this symmetry, which is not a group anymore, means. And so I think that would be also interesting to discuss. I don't know if there's any volunteers. You guys can also write to us as usual. So,
yeah, maybe something
yeah.
we could do is maybe we can put together a list of topics, further topics, and then try to solicit volunteers.
Yeah. We'll post it on Slack, and maybe we can also give a couple of references of the. And also, as we said, we are open for suggestions. So if there's something that you want to hear about, then we can also discuss that.
So I know some of the condensed matter people also wanted to talk about these dipole symmetries.
That's right. I think we need to talk about that later.
Yeah, like not
I
now,
see.
for
I
example.
see. Okay. So we need to still find someone for.
If someone will be willing to volunteer.
Mhm.
Obviously, this is a journal club, and if no one volunteers, then there's no journal club. But but we can't, we can do what we can do. If there isn't anyone jumping out of their seat to volunteer right this moment, maybe we should thank Matt for his nice talk.
Okay, let me stop recording.